Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. Today, students, we are going to do a deep dive into a fundamental topic, basic properties of electric charge. This is, the very bedrock of Unit 1, electric charges and fields. Our mission today is to give you a crystal clear, exam-safe understanding of additivity, conservation, and quantization. Let us start with a simple observation that every student must have encountered. Why do we sometimes see sparks or hear a crackle when we take off synthetic clothes or a sweater, especially during dry weather?
Yes, I have experienced this. We learn it's static electricity, right, from
Right.
friction. But where does the charge actually come from? Does rubbing create it?
Exactly. That is the fundamental question. And the phenomenon you hear, that crackle, it's the discharge of electric charges that have built up due to that rubbing. Consider this classic context. You rub a balloon on your hair. The total charge in the hair balloon system is perfectly conserved. Your hair loses electrons, so it becomes positive. And the balloon gains those very same electrons, so it becomes negative.
So the total charge was 0 before, and it's still 0 after.
Precisely. It was 0 before rubbing, and it's 0 after rubbing. The charge has only been separated. Now here is the surprising part. We see this transfer in action when a charged comb attracts neutral pieces of paper. You might think only charged objects attract each other, but why does a charged comb attract a neutral object?
That's always been confusing. If the paper is neutral, shouldn't it have no reaction?
That's what our intuition tells us. But the charged comb creates a non-uniform electric field around it. This field induces a net dipole moment in the paper. It doesn't charge the paper, it just shifts the charges that are already there.
Okay. So the positive and negative charges inside the paper separate a little bit.
Exactly. And because the field is non-uniform, stronger near the comb, weaker farther away, the induced dipole experiences a net force.
A net force. So the side of the paper closer to the comb is attracted more strongly than the farther side is repelled.
You've got it. The attractive force wins. And this pulls the neutral paper toward the comb. It shows that charge and its field have these surprising invisible effects even on neutral objects. Okay, let us now formally unpack this. To understand how charge behaves, we must know its fundamental rules. Electric charge is a basic property of matter, just like mass, but it obeys three specific experimentally proven rules. These are additivity, conservation, and quantization. To make this easy to remember, let's use an analogy. Think of electric charge like money in a system of multiple bank accounts.
Okay, money in bank accounts.
Right. First, conservation. You can transfer money between your accounts, right? But the total amount in your entire system, say 1 lakh rupees, stays exactly the same. Similarly, electric charge transfers, like when rubbing glass and silk, but it's never created or destroyed. The total charge of an isolated system is always conserved.
That makes sense.
Second, quantization. Money comes in discrete packets. Rupees, pays. You cannot have half a rupee in a single transaction.
Right, it's a fixed unit.
Exactly. Similarly, charge comes in discrete packets, which are integral multiples of the elementary charge. Third key. And third, additivity. Money can be positive, which is a credit, or negative, like a debt. The total amount is the simple arithmetic sum of all your credits and debits. Charge is a scalar quantity just like that, so we add charges algebraically, taking their signs into account.
I understand conservation and quantization from the analogy, but why is additivity so important? Isn't simple addition obvious?
That's a very good question. What's fascinating here is that charge is indeed a scalar, like mass, no direction. But unlike mass, which is always positive, charge can be positive or negative. So if you have charges of +5 units and -3 units, the total charge is simply +2 units.
Right.
This simple addition is crucial before we start dealing with vector quantities like electric force or the electric field. It simplifies everything. Now let us see how NSER formally defines this, using the precise wording you need for your examinations. Could you please read out the definition of quantization of charge?
Yes. It says, experimentally, it is established that all free charges are integral multiples of a basic unit of charge denoted by E. Thus, charge Q in a body is always given by Q equals NE, where N is any integer, positive or negative.
Excellent. So mathematically, that's Q equals N times E. The elementary charge E is a tiny number, 1.6 times 10 to the power of -19 coulomb. This just confirms that charge can only increase or decrease in these fixed steps. Now let's do a quick worked example for conservation of charge. Imagine a system with rod A, which has a charge of +8 times 10 to the power of -6 coulombs, and rod B with a charge of -5 times 10 to the power of -6 coulombs. What is the total initial charge of this system?
Okay, since charge is additive, I just sum them. So it's +8 plus -5, which is +3. The total is plus 3 times 10 to the power of minus 6 coulombs.
Correct. Now, suppose the two rods touch and are then separated. We measure the final charge on rod A to be plus 2 times 10 to the power of minus 6 coulombs. What must be the final charge on rod B?
Well, by conservation, the total has to stay the same. It must remain plus 3. So if rod A is plus 2, then rod B must have the rest. That would be plus 1 times 10 to the power of minus 6 coulombs.
Perfect. It confirms the total charge is invariant even after it redistributes itself. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now, this property of additivity is what unlocks our next major calculation tool. It means we can use the superposition principle to calculate forces between multiple charges using Coulomb's law, because the individual force contributions, they just add up vectorially. Okay, now let us discuss 3 silent killers. These are misconceptions that often cost students marks in the examination.
Okay, good to know.
Killer number 1, misunderstanding cancellation. The wrong idea is that students think that if charges have opposite signs, they will always cancel each other out when they touch.
So plus and minus always become 0.
That's the wrong idea. The correct idea is that charges cancel to 0 only if their magnitudes are exactly equal. A plus Q and a minus Q. If the charges are, say, plus Q and plus 2Q, the total charge is plus 3Q. The object will still be charged after touching.
Ah, so cancellation needs perfect equality in magnitude.
Precisely. Killer number 2, quantization versus macroscopic charge. The wrong idea here is that since charge is quantized, we should see it changing in little jumps in the real world.
Like it should be. Blocky.
Yes, exactly. But the correct idea is that the elementary charge is just unimaginably tiny. Macroscopically, we deal with charges in microcoulombs or coulombs. Here's a fact from the textbook. To get just 1 coulomb of charge by transferring 10 to the power of 9 electrons per second, it would take nearly 200 years.
Wow, 200 years.
So at this huge scale, the grainy quantized nature of charge is lost. It appears to be continuous. And the third, silent killer. Conservation means static. Students often confuse conservation with staying put. They think the charge can't move.
I can see why that might be confusing.
The correct idea is that conservation only means the total charge remains invariant. Charge can move freely, transfer between objects, flow is a current. The flow is not restricted, only the total accounting must balance.
So I need to remember that charge looks continuous on a large scale, and conservation means the total amount is constant, not that charges are static.
That is the key. Those distinctions are very important. To ensure these properties really stick in your mind, let us use some memory anchors. Here is a simple mnemonic for the core concepts. QUAI.
QUAI.
Yes. Q is for quantized. U is for unchanging, which is another word for conservation. A is for additive, and I is for invariant. Charge is invariant under relative motion, unlike kinetic energy.
Invariant, okay.
And the key phrase to summarize charge is this. Charge quantizes, conserves, and adds. Never created, never destroyed, just moved around.
I like that, just moved around.
It captures the essence of it. Now for a physical anchor. Hold your hands up in front of you. Imagine charge transferring from your left hand to your right hand. The total amount of charge between your two hands stays the same, even though the distribution has changed. This gesture, it represents the conservation and the transfer of charge. So to summarize our deep dive, here are 3 exam-safe factual points on the basic properties of electric charge. Point 1, quantization. Electric charge is quantized, existing only as integer multiples, Q equals NE, of the elementary charge E.
Okay, quantization.
Point 2, conservation. The total electric charge in an isolated system is conserved. Charge can only be transferred between bodies. It cannot be created or destroyed.
Conservation.
Got it. And point 3, additivity. Charge is an additive scalar quantity. The total charge of a system is the simple algebraic sum, with proper signs, of all individual charges in the system. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is Prof Sam, right?
Yes, ProfSam.com. Thank you for participating in this concept explainer. We shall continue our discussion on electric fields next time.